You doing the proof on your YouTube channel?
Yes. Before I start, I want to know if you see it already. There might be a small delay though.
Yeah, I don't see anything yet. What am I supposed to be looking for?
Refresh your page. It may come out when you refresh.
Okay, I see now. It says live and it's at the top.
Okay, and you see the board, right?
Proof of the well ordering principle. I see it.
Yeah, all right, very good. So a non-empty subset of the integers bounded from below has a minimal element. So this is the statement I'm going to attempt to prove. The one on the bottom is an exercise. It's a homework exercise. Okay, so here's what I want to do. I will begin with a non-empty subset of the integers that is bounded from below. So let A be a subset of the set of integers non-empty, bounded from below. All right, so since it is bounded from below, let me pick some integer that is a bound. So let n be an integer such that n is less than or equal to a, where a is an element of over A. Now let me pause here and explain what I picked. I picked an integer which is less than every element of A. Is that choice legal? The answer is yes, because that is my hypothesis. My set A is bounded from below. So the existence of n is ensured by that. Okay, so if A is an element of my set A, done. We're done. Because excuse me, is if n, not A. If n is an element of my set, then I'm done. That will be the minimal element. So n will be the minimal element. Now, the difficult case is, what if n, the n I picked, is actually not contained in A? Then what happens? So I have to ask that question. If n doesn't belong to A, if n is not an element of A, we need to identify an element of A that is minimal. Okay, so this is our goal now. So let's consider the case where the number n is not in A. This is the case we need to consider now. Okay, so let's make some space for that. So suppose n does not belong to A. Now, here is the arrangement. Let's pick an element from A. So pick, let me use a different marker because this one is running thin. So pick, let's give it a name. Let's call it X in A. Now, X is some integer in A. So here, let's remember that X is also an integer. Now, here's what I need. I need to show that either X is the minimal element or something near X is the minimal element, a minimal element. So let's observe the following. So on the number line, so I'm going to have N, and then A is somewhere, N is not in A, so let's think of A being contained somewhere in this interval. That could be infinity. So I'm picking X in A. So that's X. Now, between N and X, I have to figure out what I have. There is a whole bunch of integers, right? Because I have N plus 1, N plus 2, and then X minus 1. So if X is not minimal, if X is not minimal, there are, okay, let's see. I have to find the difference, X minus N. There are X minus N minus 1 integers between N and X. Okay, here is an illustration of that. So that the audience understands that this is a counting question. Here are two integers. How many integers are between those? So let's say this was 7 and this was 15. So how many integers are between 7 and 15? Well, there is 7, 8, 9, 10, 11, 12, 13, 14. So how many? 1, 2, 3, 4, 5, 6, 7. There are 7. How do I find that? I could say 15 minus 7 minus 1, because 15 minus 7 is 8, minus 1 is 7. So that captures the number of integers in between N and X. So there are X minus N minus 1 integers between N and X. Okay, so my claim in the end of this proof is that one of those will have to be the minimal element we're looking for. So my claim, I need to erase this board. I'm not erasing the statement that I'm proving, but I need to erase everything else. Okay, so amongst those X minus N minus 1 integers, is the minimal element of A. Now, if that wasn't the case, what would happen? None of these are minimal elements. So that means I'm picking from those elements from N plus 1. So otherwise, what would happen? From N plus 1 all the way to X minus 1, if they're not minimal elements, that means there will be some other element in A that's not above some of this. So there is an element y in A such that one of these, so that each of these, I should say, such that each of these is not going to be less than that, such that y is less or equal to n plus 1, comma, x minus 1. So if none of these are minimal elements of A, then there will be an element in A such that none of these are below it. But that's a problem right now, because actually greater than, not less or equal, just each of these is greater than y. But that's a problem, because when I place y to be less than each of these numbers, y has to be less than or equal to n. This implies that y has to be less or equal to n, and that leads to a contradiction. The contradiction is that n itself is not an element of A, but now you're putting an element of y, an element y in A that is less than or equal to n. This is a contradiction to n not being an element of A. All right, I have concluded the proof that I promised. The other version of the proof, the other case of the well-ordering principle, is left as an exercise. Thank you for coming.